I would know what it was.
Sure.
Okay, so okay. Okay, so for the 95 and 99% confidence intervals,
Yeah.
Given that you know the standard error, wouldn't you just say it's 1.96 and 2.58? Is that the answer?
Wait, for which one are you talking about? Okay, so number 3, how wide are 95 and 99% confidence intervals given that you know the standard error?
Is this when you say 2 standard deviations or 1.96 and 2.58?
I would say 1.96, but yeah, so I wonder what he means by know the standard error, because I would assume that means population level, which means we're talking about z-scores, which is why we'd use 1.96. Because, right, like the critical values are going to depend on whether or not you're estimating, because if you're estimating sigma, you use S, which means that you're using a t-table now instead of a z-table. So the critical values will be t-values depending on their sample size and stuff. But I think here where he says that you know standard deviation, that's to assume you know sigma, which means you're using z.
Okay, so I'm going to... Where exactly, like, on the table does it say, like, I've just, like, memorized those values, but, like, where does it actually, like, say that, like, those numbers, 1.96 and 2.58? Is that just, like, on the t-table, or is that on the z?
That should be on the z-table, but let me see if I can pull up one.
On the t-table for, like, non-directional, it's 1.96, and then 2.58.
499.
Yeah, I'm just saying both of them, like.
Yeah. So yeah, that's where you're getting them from the z-table. On the t-table, you're again just looking up the
That's
values.
That's what I got on a t-table.
And that is probably the infinity value, right? Like at the bottom of it.
Yeah. Yeah.
Yeah. So the infinity value on the t-table is the same as a z. What they essentially say is, because in class he kind of mentioned this, like, okay, so if you look at, here is a distribution. Let me be able to see my own screen. Oh, is this writing direct, or like, is this correct direction on the writing? Like, can you read that?
Yeah.
Okay, because sometimes, yeah, it flips it and I never know which way it's correct. Okay, so if you have this distribution, so let's say here is the z distribution. So it's nice and normal. So the z is kind of I guess z is the same as the t of infinity. So whenever you have basically infinite sample or infinite degrees of freedom or anything greater than 30, we just say, well, it's infinite because we just give you the z values. But when your degrees of freedom are small, so if we're drawing a t distribution, it would look more like this. So, and then if you have a really, like, as the degrees of freedom get higher, it starts to look more and more like the blue one, which is a z distribution.
Okay.
It's also a terrible drawing. So that's the main thing to know, is that the degrees of freedom on your, when you're using a t-table, will determine how much it looked like the normal distribution. So if the degrees of freedom are generally greater than 30, it's pretty much the same as z. But when it gets smaller, it gets a lot different. Like when you have a really small sample, you'll get a distribution that looks like this, which just says, like, we really have a lot of uncertainty about where the score is going to fall because we're estimating sigma using S, and our estimate isn't that good because it's a small sample. We just know it's not a great estimate, so we have to just factor in the fact that there's a lot of uncertainty.
So when is it when, like, the number turns out to be like 2.13? What does that mean?
On which one? So you get let's say you do a z-test and it tells you the z-value is 2.13.
Yeah, I just saw, like, sometimes when you were, like, using it, plugging in the equations, that was the number instead of 1.96. But, like, I'm just wondering, like, how on a z-score table you would find those. I'm just saying, like, how you would find those just not knowing by memorization.
Okay, so let me try to find a z-table or a t-table online.
Did it work?
T of 0.95. Okay, so here's Oh, hey, another person's here. All right, so I'm going to show you this table I found here.
This is when you look at the degrees of freedom, then when you find like a different value, like those other ones are memorized.
Yeah, so here what we're doing is you can say, okay, if it's a one-tail test or a two-tail test, and I guess we're looking at 95 here, right? So the 95%, the t-value that corresponds to 95% of the values will be, if it's a two-tail test within this point, and if it's a one-tail test, then
How do
it's
we
the
know
one.
when to use one or two tails?
It depends on the question they're asking. So
So like
if the
what?
question is like, okay, we're doing a study where you want to see if this new depression medication works better than the old one. So we're predicting that the new medication is going to lead to groups getting that medication producing lower means than groups getting the standard medication.
Say
So
like
then
for
you're
the null, you would say like mu is less than or equal to like a certain value, and then for the alternative, you would say it's greater than a certain value, and it would be
yeah.
one-tailed.
So the null here is that mu1 is, what is it? It is greater than or equal to mu2. So mu1 here is like our experimental group. So we're predicting that it's either going to be greater than or the same as this. So, and then our alternative hypothesis is that u1 is less than u2.
You're right.
So to test this fact, or to test this idea, what we do is say, can we reject this idea? So
You write
based
it
on
no.
Oh, sorry, I didn't write it there. I drew it on.
Oh,
And then
I didn't know if I was supposed to.
Okay, so there you go. So this is our null, which is that the mu1 of our group is either greater than or the same as the, this is the group getting the regular medication, this is the new medication. So this is saying, okay, we're going to presume the new medication either produces greater or the same depression scores. And then the alternative is we're going to predict that the mu1 would produce lower depression scores than mu2. But really it's not mu, it's more like, well, I guess mu is the, so here's the idea, but what we're actually measuring is an X bar for group 1 and X bar for group 2.
Yeah.
Which is
So
why
this
in
is
our
what
test statistic, this
using
is
one or
yeah. So this is the test that we're actually doing. Like when we need our t-value, we say we're observing a different score between group 1 and group 2. If this number is group 1 has a lower score than group 2, then this will be a negative number, which makes sense, right? Because we're predicting decrease. So this will be a negative. We subtract out what we'd expect to get, which we expect 0 difference if the groups are the same. And then this is the spread of the independent t-test.
Okay.
And then this thing is the long thing we walked through. Was that on Friday? So it's, you pool the variance for the population, you turn those into sampling means, and then you add them, and that's your, and then you take the square root to get to this. So it's a bunch of steps to get to this, but if you kind of understand why you're doing the steps, it's a lot easier. But I think some people just try to like brute force memorize the formulas, and that is very, very bad for you. Like you will forget them easily, especially when you're under pressure at the test. You'll switch pluses to minuses and square things that don't need to be squared and root things that need to be or don't need to be rooted.
So we shouldn't like.
I mean, I would say memorize the formulas, but more importantly is memorize why those formulas are doing what they're doing. Because if you know why, you won't make mistakes. Like you can reconstruct the formulas if you really understand the reasons that those formulas are true. Like if you like conceptually, I get like when I look at the t for the independent test, I know well we're observing a difference of the two group means. We'd expect to get 0 difference, and then we're dividing by the spread. And all I need to remember is how we get the spread, which is we get variance for each population. We do a weighted average to pool the variance. We turn those into variances of their sampling distributions. We add them up, and then we square root them to get back to a standard deviation. So this is like the standard error, or the standard error of the sampling distribution is the same as the standard deviation of the sampling distribution. We just call them different things. But this is sort of the expected average differences we'd get if you just took two
Okay.
groups from one population and compared them. You know, here's a group of 10, here's another group of 10. How different are the means? We know they're not going to always be the same. We're expecting them to be around 0. You know, they'll center. Sometimes one group is bigger, sometimes the other group's bigger. So we expect to get zeros. This is how spread out our expectations are, and this is the actual thing we observed. This is how we're able to say this observation is either unexpectedly low or not unexpectedly low.
Okay. All right. So I have another question.
Okay.
So for the effect size D, it says calculation in a one sample Z or T test and knowing which is appropriate. So basically, is it just asking that I know like which one to use? Like for T, it's when we don't know sigma, and for Z, it's when we know sigma.
Wait, sorry. Repeat that again.
So I'm just supposed to use Z when I know sigma and T when I don't know sigma. Is that what it's asking?
On which number is this? Or is that one of the 40 things? Under what conditions would you not need Cohen's D because the raw effect size would be perfectly
It's the one above
acceptable?
it, right. The one about like calculation and knowing which test is appropriate, number 6.
Yeah, it's just sigma. Basically, the one sample Z and T, the only difference is with the T, you've estimated sigma. With Z, we told you what sigma was.
Okay. And then what is the effect? And then also that one, like, what does the Cohen's D effect size tell you about the experiment? Is this for like statistical significance or practical significance? Is that like the answer is one of those?
Yeah, it's practical significance because
So
Cohen's D just says of the difference you saw, how does that compare to the differences you get at random in the population, right? So if we have a population, we know it's got a center at we're using it mu, and then the standard deviation is sigma. So here's minus sigma is another. So this is the population, but when we do our test, what we're comparing isn't the population, right? We're saying we have some mu x bar of our null, and then we're sketching out this distribution, but that distribution is sigma divided by square root of n. So how spread out it is dependent on n. So if I take a small sample, the spread will look like this. If I take a huge sample, the spread will look like this. So, the probability of getting a different score, like let's say I observe, this is the true value of mu, and I observe a value here. Like this is my alternative group. So sort of the one sample case. You know this stuff about the population. Here's my group. So in this case, if I'm looking at like p-values, right, it's sort of the probability of getting an event this extreme. So if I'm here, which would also put me there, then my p-value is in a sense all this area, right? So that's a pretty large area relative to over here. My p-value is whatever from this distribution is not captured here, which is almost 0, right? Because this whole distribution fits in this really tight area. So the p-value you'd get here would lead you to say this effect, has a greater p-value here than it does here, even though the raw difference is the exact same. So we haven't changed how different our control condition is from our experimental condition. They're the same difference, but the p-values are going to be changing depending on how big of a sample we take. So that's why Cohen's D is, the thing you got minus mu, but instead of dividing by the standard error, we take sigma. So that says it doesn't matter how big of a group you collected. That won't affect Cohen's D.
So it's basically just saying Cohen's D is just when you're not considering the population size?
Not the population size, when you're not considering the size of the sample you took. So what you're trying to do is get away from the fact that
like you're not considering n, like it's not whether like n is 50 or n is like 1,000. You're just trying to do it like if it was any number.
Because what we want to do is say, okay, you found a difference. Like let's say it's I give you a pill that makes you an inch taller. So it's like, okay, you found a 1-inch difference. If I divide that by your standard error, if that group that took pills was a group of 2,000 people, then relative to the standard error, because it'll, it's the null distribution will look really tight like this, it'll say, well, there's a really low probability that's random. But that doesn't mean that the effect's bigger, because I could have done that exact same study, found the exact same 1-inch difference, which is what we're kind of seeing here. But if I took a sample of 16 people, the p-value, I probably wouldn't even be able to reject the null in this case, because there's all this probability of randomness giving me that value. But that doesn't mean this effect is any more or less real. It's just that we didn't have the statistical power to find it. So once you find an effect, what you want to do is just say, give me that distance score and say how much does it matter relative to what the population was already going to vary on its own. So don't consider the fact you took a big sample.
What would be like a sample like sentence question asking for finding effect size?
I mean, it would be stuff like this, like essentially.
Would this be like a one question type of thing, just because like it's multiple choice, like, and you wouldn't be able to do like 50 steps of a problem in like one question? But
probably, but
so would it just be like
okay? So I could say, like, I could ask you, would taking a larger sample have, or which of these would be more affected by a larger sample, the p-value or the Cohen's d value? In which case, it has to be the p-value, because when you're doing the statistical test, we're using n here. Here, we don't use n at all. It doesn't matter how big of a sample you took. We don't care.
By p-value, do you mean pooled?
No. The p-value is so.
What equation is that?
Case. So that we don't give you an equation for it. We just talk about. So if this is, oh, I almost lost that pin. So let's say you do a test where you're doing a one sample test again. So in the case of one sample, let's just say this is our sampling distribution here on top. So we've got u sub x bar, and this is sigma square root n, negative sigma square root n. So this is sort of your expectations, and then I tell you, so you can kind of set up your expectations, and I say you observe a value that is exactly sigma square root n, right? So that's the value you observe. You take a group mean and you get that. What you could do is use a z-table and say, okay, well this is, we know it's going to be a z of 1, right? Because 1 standard deviation. So for a z of 1, how many scores are greater than a z of 1, and how many scores are smaller than a z of 1? These two, you add up the probability here and the probability there, that is equivalent to your p-value, which is what you can think of as, this is the probability that randomness would give me a value this extreme or more extreme.
So if you were doing like the 95%, it would be like 2.5, 2.5. Is that percent? Is that like your p would be 5%?
So your p is actually dependent on what your x bar is, right? So if I can, like, let's say, like in the case of,
are we supposed to calculate p, or like?
You don't really calculate p. What it is you kind of just can look it up from the z-table. Like, that is really what p is trying to get across. It's saying when you observe any given z value, right? So a z of 1.96, how many scores will be more extreme than 1.96? Which means if we're calling this 1.96 right here, like let's say that's our cutoff. So more extreme means more negative or more positive. So how many scores are going to be out in this region, plus how many scores are out in that region?
You just say 5%, right?
Yeah. So your p-value, if you got a z of 1.96, is 5%, because that's the chance of getting a value either that large or that small when you're doing a two-tailed test of observing something like that. So if you get a z of 2, then your p-value is less than 5%, right? Just because we know 1.96 is 5, so this is something less than that. And you could look up the number 2 on the z-table, which will probably just tell you, here's how many people are smaller than 2, so it'll tell you all this probability. And let's say it's, let's say it's 2%.
2.28%?
What is it?
I just looked it up.
Oh,
I looked at area non-B for B.
Yeah.
And then, it says 0.0228, so that's 2.28%.
Yeah, so that's 2.28 here, but the value of getting something that extreme is actually that times 2, right? Because there's also a chance of getting a negative 2 value.
Okay, so what was the question you asked again about? Yeah, what was the first question you asked again?
So I was just saying
about between pooled and between P and D. What were like the?
So what's happening is that the p-value is affected by the sample size, right? So this is square root n. If I took an n of 50 versus an n of 500, the p-value will change greatly, right? Because the distribution I'll be talking about won't be this purple one anymore. It'll be this new dotted purple one. So when we look at that one, it'll say, oh, your value here is much more unlikely. But the raw difference we're observing from the center has not changed. So that is why you care. That's the difference mainly between the p-value and d. P-value is factoring in the size of the sample you're talking about. Cohen's d doesn't care how big the sample is. It just says, well, you've observed a raw effect, which is 2 points increase, and now divide that effect by the average spread of the population to give me an idea of how much of a difference that would be randomly happening in the population can you make to these people. Like, imagine I do a school intervention where I say, if everyone buys this $1,000 laptop, I can run a statistical test and show you that you will improve in scores. But then I tell you the Cohen's d value is, Cohen's d is equal to 0.01. That means if you did this effect, the expected result is 1% of a standard deviation improvement, which is very, very small.
Okay. And that wouldn't be very statistically significant.
Well, it could still be significant, right? So if I took a sample of 50,000 people, the p-value would be tiny, right? So here, like, let's say this effect right here. Let's pretend this is a small effect. So this effect here, if I'm taking this giant sample, this is the distribution, this is the null, so it's really unlikely. So the p-value is, probably something 0.001. Where if I take a smaller sample, it might be 0.05. So the p-value is changing, but in both these cases, because this difference, let's just call it, that's 5. That 5-point difference doesn't change Cohen's d. Cohen's d gives us the same answer every time.
Okay.
Because Cohen's d is not letting us, it's not, what's happening here is we're taking advantage of the fact that we know how statistics works. And so we know that the bigger the n we have, the less variable our null distribution is, therefore it's easier for us to take this effect of 5 and reject the null. If we take a really small sample, we might not be able to reject the null with this difference. So it has nothing to do with whether or not it's statistically significant. It's just saying that this is how much you should practically care about this effect. Like, this is how much of a standard deviation improvement, or I guess.
I thought you're not supposed to care unless it's like 0.03, 0.05, 0.08 or something, right?
Well, so those are the rules of thumb of talking about an effect as small, medium, or large. So this would be a tiny, tiny effect, but it could be statistically significant, like a p-value of 0.001. If you take a large enough n.
There's a cutoff for so you need a p and a d to figure out if it's statistically significant?
No, you need the p to tell you if it's statistically significant, and the d tells you if it's practically significant. Like, okay, p just says, are these reliably not the same thing? And if you can say these are reliably not the same, then we're rejecting the null, which is they're the same. But that doesn't tell us how much different they are.
So basically anything above 0 for a p-value means it's statistically significant.
Wait, anything above
0?
No, for p-values, anything less than 0.05 means statistically significant, if alpha is 0.05.
Okay. This is for a t-test.
For pretty much all the tests. Like the test, you just set alpha as the rate at which alpha, and it's not even a rate. Here's a way to think of alpha. Like, here's how I like to explain it. Alpha is a way to say, here's how much evidence I need to convince myself. So we know scores are going to vary, right? Here's, let's say this is our sampling distribution. So this is what we should expect to get from groups of size n. Let's just say here n is 50. So this fully describes our expectations of what a group should get. And now we can say, okay, this is what is going on in the population. So in the case of the 1 tilde z, we know the exact population values. Say, okay, we know what's happening in the population. Now I'm going to take another group, and I'm going to do some intervention to them and see if they're different than the population. And before you do it, what you're supposed to do is set alpha as this is how much evidence I need to be convinced that they're different. So the smaller the alpha, the more evidence you need. Because alpha is your false alarm rate, right? Because I could set alpha to 0.6, which would basically say everything not in this little center region is going to be convincing to me that it's different, right? So if it's not right around mu, then I'm going to say it's different. So I could set alpha really high. But what I know is that I'm going to make a mistake 60% of the time, because 60% of my scores are in this region where we know they're going to be from the population distribution, or from the sampling distribution. We know there are going to be a lot of scores here, but we're willing to conclude that they're different. But what that means is that all of these, so every time I get a score, let's say if I observe a score right here, right, from this distribution, right, so anything in this purple region with my really large alpha value, what I'm saying is 60% of the scores that I know are going to happen, I'm going to make the conclusion that they're from somewhere else, even though they're not. So I'm going to be wrong 60% of the time. But when alpha is smaller, so like alpha is 0.05, what we're doing is we're setting a more stringent criteria for ourselves. We're saying, I need to get something very unexpected to be convinced that this thing that I'm looking at is not from my population. So when you set alpha to 0.05,
So this is just like for mistake, like so you don't make a mistake by having some like random thing in your population that you're considering in your data.
yeah, we don't want to look at randomness and be like, oh, that's our effect. So here, when you set 0.05, which is kind of the standard criteria that most people use, that's saying, okay, we know most of our scores are going to be here in the middle, so if we get a score in here, we're not going to be convinced that we found a difference. We're going to say that it's coming from this population, because it's likely to be from here, right? If I get a score right there, it's not that unlikely. Randomness could give me that a lot. Randomness won't give me values out here that much. So in the case of a two-tailed test, I'm saying I need to get a value out in this region somewhere, or in this region, to be convinced that my X bar score that I'm looking at, so either of these can be X bars, they have to be out here to convince me that they're not from this population, which will be in error 5% of the time. So that's why alpha is actually the same as the type 1 error rate.
Isn't like beta type 2 or something?
Yeah, beta is type 2. That's the chance of missing an effect. I don't think you guys need to know much about that, but yeah, beta is type 2 error rate, but I don't know if he plans to talk about power, but power is kind of your ability to find an effect.
Okay. All right.
The power is a lot more complicated. It usually is one of the things that throws students.
Okay. Thinking about another question to ask. Okay, I have another question. For number 12, why is hypothesis testing proceed by testing a null hypothesis rather than a research hypothesis?
Hint, see textbook. I don't know exactly what the textbook says, but I know, like... So the problem is, you can't really...
So research hypothesis is the type you use in like a regular like science class. Like, it's basically the opposite of a null hypothesis, where like, if we do this, this is going to happen, right?
Yeah, so you're testing, did this thing we expected to happen?
So is it because it's easier to reject the null hypothesis? Is that why we use that in statistics? Is that the answer?
I would presume it is, but I would look exactly what the book says, because I know the books will sometimes have specific reasons that he wants you to say.
Okay. How would you compare an independent t-test and dependent d-test computed on the same data?
Oh, okay. Was this a number? Because that was a lot of... Wait, is this one of the numbers, or is this just an outside question?
No, it's number 15, like on the 40 thing.
Compare an independent t-test and dependent t-test computed on the same data. Okay, so the degrees of freedom are going to change. What else is changing? Like a lot of stuff is changing. Like you're kind of, some of this is just literally just like looking at the formulas and like, okay, these are all the things that are not the same between them. Like let's see if I can pull something up. What was that?
Can you go through what are not the same about them?
Yeah, let me try to find the slides here. Oh, these slides take so long to slide through with PDFs. I think a lot of it is the computation of the thing you're observing. So I can probably just wipe all this out.
Well, dependent is like the
related,
or is dependent is like the related pairs, matched pairs, that thing, and then so. But independent would be like different. So then why would you do the same data on them?
So you could imagine a study done as a independent or dependent test if you just collect the data differently. So let me just finish writing this out. So so I do this a lot of times in like my studies because I do things like a memory experiment. So let's say I want to compare you learning words in 2 different ways. So I'm going to have you in one case, you'll just read the words, and another case I'm going to have you generate the words. So you'll see, like instead of.
So you could basically, is this like, you could basically say that since I'm the same person, like one is dependent on the other, but then you could say that they're completely different things, even though I'm the same person, and test them independently. Is that what it is?
Yeah. So this study, you can imagine. So I'm comparing, in this case, reading words versus generate. So cat dog versus cat D blank G. So you have to fill in the blanks. And I can do this study as this is 10 people learn words this way and 10 people learn words that way, in which case I would be doing an independent test, right? Because this would produce an X bar 1 and this produce an X bar 2, and I could plug them in here. But I could do the exact same study where you're in my group, and now you're going to learn 20 words. You're going to learn 10 this way and 10 that way. And so what I'm going to do is on each of your scores, for you, I'm going to calculate a different score. So how different was your recall of these versus those?
Okay.
And then what goes in there is the average difference score. So that's participant 1, this is participant 2. So everyone produces a difference, and this is equal to, read minus generate. So the difference. So for each of the people, I can compare, let's say you got 10 words, or let's say this is 5 versus 8. So you have a score of 3. And this is 6 versus 9. Again, a score of 3. And this is 5 versus 6, score of 1. So then you each have a different score, and what goes in is the mean difference. So I average these. So what's that? 7. Oh, why did I make the math so ugly? Let's pretend it was, let's give them all 3. So then the average is 3. So the mean score is what's going in there. Well, okay. Here what I'm doing is just saying I have 2 averages. That's 5, that's 7, and then those go directly in. So it's kind of the difference in the way you're computing them. And then the degrees of freedom change. So this one, the degrees of freedom is in pairs. So the number of pairs minus 1. And then here the degrees of freedom is degrees of freedom for group 1 plus degrees of freedom for group 2. And degrees of freedom for any group is the number of people in the group minus 1.
Okay.
So the degrees of freedom would be very different here. If these were 10 pairs of people versus 2 different groups. Here we'd have 20 people. So 20 minus essentially 2, we have 18 degrees of freedom. Where here, if we had 10 people doing it twice, we'd have 9 degrees of freedom.
Okay. Okay, that makes sense.
Generally, we talk about these as being more powerful tests.
Which one?
The dependent.
Okay, because it's like not, you have less chance of finding something random from different people.
Yeah, because each person kind of serves as their own control, so that ends up being a lot nicer for you statistically. Where here, like the fact that this group got 5 and 7 could just be related to like this group could have just got people who just weren't, they were tired, and these people were like these people just come in more after lunch, and these people come in more in the morning, or just randomness sometimes gives you groups of people that are different. Where here it doesn't really matter what randomness gives you because everyone is in both conditions. So if you happen to be a really high performer, because I'm not looking at your performance level, I'm just looking at the difference between the two, I kind of factor out the individual characteristics of you don't matter because all I need is how different you did in those 2 conditions. We hear the fact that you're really awake and I'm really tired will make our scores different for reasons that have nothing to do with our study. So there's a lot more noise in this. we're kind of taking away noise by factoring in that we're comparing you to yourself instead of you to somebody else.
Okay. Next question I have, let me see. When it says for number 16, identify possible type 1 and type 2 errors in experiment, would this just be like they give you an example and you have to say if it's type 1 or type 2? Because, I mean, I don't know how to do that, but.
So that's number 16, identify possible type 1 and type 2 errors.
Yeah, is this just in actual examples? Like they would say like, say like you failed to reject and it was actually right.
Yeah, like you failed to reject null, what error could you be making? You couldn't make a type 1 because type 1 is rejecting incorrectly, so it'd have to be a type 2 error.
That's basically what it's saying, is if in an example, is that, I'm just wondering.
Yeah, that's what I imagine it'll be asked. Okay. Or something like that. Well, if you conceptually get, that's, you know, type 1 is when you reject when you shouldn't have, and type 2 is when you fail to reject when you should have rejected.
And like what factors affect them?
A lot of it is sample size. So sample size and also raw effect size will affect it. So again, it's probably better to draw the stuff out.
Was like the numerator of the
the top part. So the x bar minus mu over.
What's the difference between that? Like the top. So what's like the difference between the raw effect and the Cohen's d?
The difference in the raw effect is the raw effect doesn't take into account how spread out the scores are. So I could take, let's say everyone's average, I don't know, I always follow the height, but let's say the average height is 6 feet in some sample basketball players. And now we say we gave them all a pill and now their average height is 6'1". So the raw effect size is 1, but I can take that exact same group of people and measure their height in millimeters, and the raw effect size would go up even though the difference between the groups didn't go up. So raw effect size in lots of ways, the raw number
when would you want to use
in the scale of measurement you're using.
Like when would you want to use raw effect size over the Cohen's d?
I'm trying to think of cases. I mean, I never see it. I always see Cohen's d, but I'm trying to think if he has good examples of when raw effect size is.
I don't think this was on like this 40 question thing, but I think it was on like the, what's it called?
I mean, raw effect sizes are good because people understand raw effect sizes more intuitively than Cohen's d. Like if I tell you I increased height by 0.2 Cohen's d, you don't know what that means. But if I say I increased height by 2.5 inches, you can go, oh, that's pretty, you know, that gives you a magnitude of the difference because you understand the scale. So what you lose when you go to Cohen's d is you lose the scale of measure. Like you lose whatever we were talking about.
But
so
you're getting it to be more precise for your specific data for n.
Yeah, well, it gives you it's not that it's more precise because it's the same difference score. It's just that it gives it to you in a metric that you can compare to people who are measuring things on other scales. Like I could say like I could compare the effectiveness of Prozac to decreasing depression to the effectiveness of Lipitor for reducing blood pressure. Which of those is the more effective medication? They're completely treating different things. But in Cohen's d terms, if I say, okay, the Cohen's d of Prozac is 0.3 and the Cohen's d of Lipitor is 0.5, we could say Lipitor is a better medication than Prozac. Prozac is not as good at treating its problem as Lipitor is.
But for like the raw score, you couldn't compare it because they would be completely different measures. But for this one, you're putting it on scale to their like specific spread.
Yeah,
so you're just kind of comparing to a fact.
Yeah.
Right.
So here, we're talking about two totally different things, but we could still talk about how effective each of them is.
But if it was the raw score.
But yeah, with raw scores, it wouldn't make any sense because you'd be like, oh well, it has -2 because whatever the depression scale is out of 20, and this has -35 because whatever blood pressure thing. It's like it lowers your blood pressure 35 points. So you don't know what if I showed you that Prozac is -2 effective and this is -35, you wouldn't have any idea how to tell me which of these is better because it could be that this is a 0.5 effect and this is a 0.2 effect depending on how spread out the scale is.
So
how variable blood pressure is.
when you're doing a raw score, you're being basically in the units of whatever you're testing. Like if you're going to be doing in like height, it could be like inches or centimeters or whatever you're going to measure it in. And then when you're doing blood pressure, it could be like in a completely different unit. So you can't really put them on in a comparison about which one is better. But once you do the D, then you can compare relative to the other one.
Yeah. I mean, but it's kind of weird usually to talk about Cohen's D in isolation, but like if you're a funding institution and two people have different treatments, like one is saying, okay, we're going to handle school bullying and we have an effect size of, we can have a 1.2 effect size. So we have a huge decrease in bullying. And someone else says, well, we have another program that makes kids healthier. So this is, bully, and this is health, whatever health means. And their effect size is 0.4. Who do you give money to? In lots of ways, you look at for yourself which of these, if you see these are equally valid problems, you would give money to this group because you would say, well, they're having a huge effect. Whatever they're doing is really affecting this thing we care about. And if we care about these things equally, this is where you pour your money because this gets an effect that's much more impactful than this effect.
Okay, that makes sense. Thank you.
No problem. I think you asked really good questions because I noticed a bunch of people watch these afterwards.
Yeah, so I'm probably wondering this stuff too. I mean, I hope. If I'm the only one wondering it, that's not good.
No. I think just people are worried to ask, and as long as they see somebody asking, they're like, okay, good.
To all you people watching this on YouTube.
Yeah, exactly.
I'm the only one, so participate.
That's what I say.
Okay, so I don't know. Here's some interesting question for 19 that says like, "What's the beef?" I don't know what that phrase means, but it's so would you like prefer an effect size and confidence interval if you're a researcher, because like with the null hypothesis, it's like very broad and like easy to like reject the null, but once you move on to effect sizes and confidence intervals, it basically makes it like more specific. Is that what it is? Like you're getting more information from that rather than just like a general like, well, it does something different or doesn't, because that's basically what the null is saying. It's like on a broader level, right?
Yeah, the null is very like, it's not that informative to say you rejected the null. That just means statistically these are not identical. But it's kind of the thing I was showing you earlier with p-values. Like the p-value can change radically. With the same raw effect, you can have p-values that get bigger or larger depending just on your sample size. So like that shouldn't make it more interesting or a more valuable effect. So that's why when you talk about confidence intervals or effect sizes, you're telling people, well, here's how much you should care about this. Like here's how practically useful this thing is that I've just found. Or how practically, harmful it is. Like let's say you study the effects of smoking and the effect size on life expectancy is like, 2.1. Like it lowers your life 2.1 standard deviations for smoking. So it's like that is a big effect. You want to tell people, hey, stop smoking because look at this research. It has a huge effect. Like if you tell people the p-value of smoking is 0.001, what the hell do they like that? It's not clear what to do with that. And it could just be that it's tiny because you have a sample of 50,000 people. Or it could be that you took a sample of 10 and your effect size is so huge that you still get this value.
Okay.
So someone could look at this is, let's say smoking has an effect size of 2.1. So again, these are just numbers I'm making up just to kind of prove, make a point. But in general, this is kind of how it works. Versus secondhand smoke has an effect size of 0.01. And let's say I do a secondhand smoke study with 50,000 people. Right, so I look at 50,000 people who live with smokers, and here I grab 25 people who smoke. I might get the same p-value for these two studies because what's happening is that this huge effect is able to be found with 25 people and still have a low p-value. So if this is the distribution, it's a pretty wide distribution, or actually it's not. The shape of these will be identical. So when we're talking about the sampling distribution, it could look like this. That's mu sub x bar This is standard error of the mean. The same for secondhand smoke. So when we talk about that's got its own mu sub x bar. This is the standard error of the mean. So these two will look identical if we find, here's where our effect lands out in the corners. We get the same p-value because these are both very unlikely. But the problem is when you look at the population level, it might be that in the population, health looks like, trying to think of a good way to show it. It's not really a great way to show it, but essentially the population is much wider here. So we're getting that p-value. Again, this visually doesn't look right, but let's just say. So what ends up happening is that the population difference between non-smokers and smokers is really pronounced. So you're able to find differences pretty easily. So you only need small samples, and you can still get big effect sizes. Well, here, the reason this distribution looks like this is because of this giant N. Like the real population down here is going to be way more spread out because we're dividing it by whatever that sigma is, divided by square root of 50,000. Well, here, the actual population is going to be much less spread out because we're taking the sigma and only dividing it by 5, right? Square root of 25. So we're just saying the p-value doesn't tell you really how much you should care because you can get the same p-value if you just run a really small effect size study with a huge sample versus a really big effect size study with a small sample. So because those interact with each other, because the effect size will in some way determine the p-value, but also the n. So the bigger the effect size, generally, the smaller the p-value, but also the bigger the n, the smaller the p-value. So here we kind of have like, this is driving us to find a big p-value. This is driving us to find a small one. Here, this is driving us to find a small one. And that one's driving us to find a huge one. So these kind of cancel each other and you get the same p-value. But the effect size more clearly says, if you're a smoker, you should really stop smoking. Secondhand smoke seems to not do all that much to you.
Okay.
Like you shouldn't be that worried if someone in your house smokes, but if you are smoking, be very, very worried because it's going to really shorten your life expectancy.
For practical significance, the effect size is more important to look at. And then if you're just looking at statistical significance, you look at the p.
Yeah. Yeah, p-value tells you statistical significance. It says different, this is unexpectedly different or not, but that's about it. Where effect size tells you, okay, now that we know they're unexpectedly different, how much do I care about this difference? Or what's the size of this difference?
You're going to share with people, if you're giving a study and you're presenting it to them, would be the effect size, basically.
Yeah, the effect size, well, it depends. Like if you have a greater, like the effect size is huge, yeah, you want to tell everybody. But lots of people will run studies like this and just talk about p-values because they don't want to talk about the effect size because they found a tiny effect. They just were able to find small effects because they have a huge sample size. But so technically, you want to be talking about, yeah.
But p because basically p is just telling you if it had a change, that like there was a change, and then so wait,
yeah, what's the chance randomness would give you this?
Basically, null is saying there was a change. P is saying there's a statistically significant change, and then the raw effect is telling you actually how much there was of a change.
Yeah, and the effect size tells you a metric that you can compare to other people's effects. Because the raw effect size tells you like 2 inches height improvement, and you can say, oh, I know how to use that information. But now if I'm a medical company and I want to fund either a pill that makes you taller or a pill that makes you smarter, and I know people care about both of those equally, and the smarter pill has an effect size of 1.2 and your height has an effect size of 0.4, I'd say put the money in the smart pill because it's got a bigger effect. People will care more about that effect.
But raw effect, you can't compare to it. You can't compare like smartness and tall people.
Yeah, because you'd be like, well, it made them 2 inches taller versus 5 IQ points higher.
Okay. All right. I guess we do need to know what power is because it says it in this guide.
Which number?
20.
Define statistical power in words and symbols. Why are researchers concerned with the power of a null hypothesis test?
Like 1
Did you ever
minus
talk about power in class? I thought he was dropping the power. I thought he even specifically said we didn't need power.
I was looking at like the lectets and then I saw that and I was like, oh, I don't think we talked about that. But
yeah, we haven't, and power is kind of confusing.
He sent this yesterday, so I don't know if he like made it yesterday, or if it's just another thing he took that was like from before. What do you think?
Yeah, it's possible. Let me see. I'm looking at emails you sent. I don't. So I think. Let's see. What does he want you? So what number is that again?
20.
20. Okay, just find statistical power in words and symbols. I think what he wants is this, because we didn't talk at all about how to calculate power. Because that's, I mean, it's not hard to do. It's just it's conceptually hard to understand. But this is what I think he means. Power in symbol is just this. Power is 1 minus beta.
And beta is a
type 2 error rate.
Yes, type 2
which
error.
Is
when you failed the deck,
yeah.
but it's actually improved or did something different.
Yeah. So we said there was no difference, but really there was.
So it's saying to talk about it in words and symbols and why you are concerned with power. Do we actually need to know that? Like, I don't think we learned about that, did we?
Not really, but here's the main point is that power is your ability to find an effect if it's there. So the reason you would care about power is because if you run a study and you don't have the power to find an effect, like this is just going to be some probability, right? So it's 1 minus beta is some rate. So let's say it comes out to be 0.2 versus 0.8. What that means is if you have a power of 0.2, that means when there's an effect there, you're only going to reject the null hypothesis 20% of the time. So 80% of the time, you're going to miss the effect, even though it's there. With 0.8, you'd say, well, if you have a power of 0.8, that means 80% of the times you do this test, you will find the effect when it's there. So you're only going to miss it 20% of the time. So that's why you care about power. Like if you're a researcher and I said, okay, here's a bunch of money, do a study. What?
Like the 0.8 is better because basically you're going to miss less things if you have a higher power. So like the higher the power, the less you're going to miss the effect size. And obviously if you're going to try to prove stuff to people, you want to know it as much as you can.
Yeah.
Is that what it is?
Because why, if you had a really low power, it wouldn't even make sense to do the study. Like if I tell you your power is 0.1 before you do the study, that means even if you do the study perfectly and the effect is there, you have a 10% chance of seeing it, or a 10% chance of making the correct conclusion, which is that you should reject the null.
It wouldn't be as much like if you had to like invest a lot of money in an experiment, it would kind of stink because it would be like more likely that you would miss what was happening than you'd see what's happening.
Yeah. So it's like, okay, why would you even look for it? It's like if I told you to like go to the ocean to find coins, and then it's 0.002 chance you're going to find anything. Would you invest a lot of time doing this to basically, even though there are gold coins in there, you're not even going to find them. There's almost no chance you're going to get them. Why would you waste time doing it? So you want to design studies with lots of power, which means that if the effect is there that you're looking for, you will be able to detect it. And I think that's as far as he wants you guys to understand power. Because, I mean, in the past, we've had people calculate power.
In words, you would just say 1 minus beta?
No, this is the symbols I think he wants. Like
in words, what would you say? 1 minus type 1?
I would say in words, the reason, like what is the explanation of power? Power is the probability you will find an effect when it is there.
Wait, so beta is type 2 though, right?
Yeah. So power is 1 minus beta.
In words, that's how you, I'm just asking because it says words and symbols. So I'm wondering if there's like a.
In words, I would say that power is your probability of finding an effect when it is there. That is the kind of words. Like I think what he means in words is like, what do you understand power to be? And that is the understanding you should have, is that power is the probability you will find an effect when the effect is there.
Okay.
Yeah, power is very different. Power, you calculate it presuming that the effect is there, and then say, okay, well, assuming this effect is real, will I find it?
Okay.
And then you can calculate that number, which is just like a combination of stuff you've already done, but it's just a lot of steps. So I think he's skipping it for this class, or it might come back right after the midterm.
Okay. Next question is number 27.
Okay.
Saying, so isn't the 2 means with the standard error of the mean like bigger?
So it's this. So this is the what is it? What was the number? I keep losing the numbers here.
It's number 27 on the.
Okay, standard error is differences between two means. Yeah.
And then the standard error of the mean is just.
Yeah.
Yeah. So isn't the standard error of the mean smaller than the standard error of the difference?
I guess let me think of how they're calculated. And then this is pool variance. Does it end up smaller? I would kind of want to, let's see to walk ourselves through it. Okay, so
it was.
And that gives us pool variance. Then we do pooled over in. And that gives us it's hard to say if it'd be different. I'm trying to work it out in my head here. So we're basically just combining those two, dividing both by n.
I found it. Wait. Standard error of the difference between two means is larger than the standard error of the mean. I think it said it in the lectet.
Oh, okay.
So, but why is that?
So it's a lot of just that we're adding all these variances up. Well, here we're taking the raw s and dividing by n, or yeah, I think that's the main thing.
Okay.
Because the variance of differences between mean is the combination of their variances, or the addition of their variances. So this is the, what do you call it? The sum something law, sum power law. I forget the exact name of it. It's in the slide somewhere, but it's essentially, this is why you, so if you want to find the variance between pulling two samples and looking at the differences, the variance of that is adding up their variances. So I guess that's why it's bigger, because you're adding two variances together to calculate this, where the other one you're not.
Okay. Sounds good. The next question I have is 28.
Okay.
So it's saying, how do they differ? Would you just say the t-test and a Cohen's d differ? Because for t, you're dividing by a sample, like,
well, so
there, and then
yeah, because if I tell you here's a distribution, and I say you observe a value right here, let's call that, that's x bar. So this Cohen's d will give you some number, but you don't know if that's statistically significant. You could just tell me here's the effect size, but if I say is that a statistically significant effect, you have no idea. Like, it's just not enough information yet. You couldn't tell me that this is statistically unlikely to be happening by randomness, because we didn't sort of look at what randomness would give us. We're just saying, well, at the population level, this is what the population scores look like. This is how different our group is from the population values, D. Like, this is how much of an effect it had. I think lots of times the book will do like the absolute value. Generally, you don't give negative effect sizes.
Okay.
You would just say it decreased it with an effect size of 0.3 instead of saying negative 0.3.
Okay. And then, but then how would the results of Cohen's d differ from the results of the t-test?
Well, they differ in that they're giving you different information. The t-test is telling you whether or not this is a statistically reliable effect. So we're turning this population level stuff into a sampling distribution, which will have a much tighter spread, right? And then this is the standard error of the mean, which is sigma square root n. So this same effect here, we take that same value, just move it down here. That's the x bar we got. The p-value is going to be very small, so now we can say the p is less than 0.05. we can be happy that we've found an effect that is statistically unlikely to be due to randomness. So that's what this is telling us. Our t-test, we actually have to do all the steps here, but once you do all the steps, what you get back is some t-value. T is equal to some number. You compare that to the table. You have some degrees of freedom of n. You look it up on the table, and then you make the conclusion that this is, just visually looking at it, that would be a statistically significant effect. So they give you different information. This says your group mean is different enough from the other group or the population that we can be convinced this is not pure randomness, or at least it's unlikely to be randomness. But that's all it's telling us. This is telling us, here's how much you should care about this difference you looked at. Here's how much that difference seems to matter when you compare how much people just randomly vary on their own.
So it's saying like why do you need both of these?
Yeah. So this is like, the conclusion here is just like different. So that's all this is saying. Like, these are different or not different. And up here, the difference is like care or don't care. Like, how much stock should we put in this result? Like, you don't just say we found a significant effect, therefore we should all be doing this. You say, well, okay, we found an effect of this intervention or whatever it is you want to be doing. It seems to be affecting people. And then Cohen's d tells us how much of an effect did it have on them. Like, how much of their normal variation, relative to their normal variation, how much did your effect change them? Because if your effect is a tiny fraction, or I guess I should be doing this. So if it's a tiny fraction of the random variation that's already going to be happening, that means that we're not really moving them around that much. Like, right? People are already randomly going between 5'9" and 5'10". If your intervention is, I can get you from 5'9" to 5'9.5", it's like, well, that's not that big of an effect relative to how much people's heights vary just for other reasons. But if I could tell you, you take this pill and you can go from 5'9" to 6'2", like, that is a giant effect. And based on how much people's heights vary, that is a huge change in the natural variation of heights. That's going from here to out here. And if you can have that kind of effect, then that's something to care about or something to think about.
So basically you want to see if the T obsolete or whatever that OBS thing is like bigger than the T critical value. Mm-hmm. And that's how you decide if it's rejecting the null or not. And then you look to the D and see how big the number is.
Yeah. So if you did this, like, you just get some critical values here, and that'll just say if things are in this region. So, right, this region extends technically to infinity, right? Yeah. Just getting narrower and narrower on both sides. So if we're out in this region, then we can say this is very unlikely. Like, randomness shouldn't give us this kind of score. It doesn't look like it'll ever happen. This is where randomness gives us. Randomness gives us a bunch of scores around mu sub x bar. But we got to think that's very, very different than mu sub x bar. Statistically, it's very unlikely. But that's the only conclusion we can make. Because this is taking into account n. So if this n is, 100,000 people, let's say this was a 50,000 person group. If it's 100,000 people, the distribution looks something like this. So the critical regions are right here, and then they just go to infinity. So this same difference of x bar to mu sub x bar, this difference hasn't changed at all. Like, how much we should care here is not changing. But our p-value is radically changing. So here it's a pretty small value. Here it's like almost 0. Okay. So the chance of randomness giving us that is very different in these two cases. But that's just because randomness is in many ways dependent on how big of a group you're taking. Because the size of our group will affect how different each sample will be from each other. So we can become more convinced of this effect being a real effect and that it's not statistically noise, or it's not a statistical error. It's not alpha. Or at least it really doesn't look like alpha. But it could be. It's a very, very small probability of being alpha. But much more likely is it's an effect. But then we go to Cohen's d to tell us, well, how much of an effect did we actually have? Like, did we move people in ways that they would care about? Like, would people notice our intervention? Because you could do the same thing if you observe a value. Let's say we did a different intervention that wasn't as effective and it gave us an x bar value out here. So transfer that down here. In this case, we would fail to reject the null. in the 50,000, let's say this is the smaller group case, right? We're failing to reject the null because we're not in the critical region. And then if we just run the same exact study, find the same exact difference, but did it with 100,000 people, we would say the p-value is very small. This is statistically reliable now. But Cohen's d doesn't change. Cohen's d here is just, right, we're going to calculate that difference and then divide it by sigma. So Cohen's d got a lot smaller for this second X bar group for the less powerful intervention. And that's also a way you can compare different interventions. Like, let's say there are 3 people who have programs to reduce depression. And if you look at the Cohen's d scores of them, you would just choose the one with the largest Cohen's d. You'd say, okay, you have the biggest, you have affected people's depression the most. So therefore, you're doing the best job at reducing depression.
Okay. I have one of the questions that kind of like goes with this.
Okay.
It's 36. That what factors affect a t-test but not a Cohen's d? So for t-test, population size affects it.
Yeah, that's a big one.
Whatever, the sample n. Right. Yeah. And then for like, and then what other factors affect a t-test but not a Cohen's d other than n?
So he might say degrees of freedom, but in many ways, degrees of freedom is just another effect of n, right?
Okay.
I'm trying to think of other things that can go. I think in that case, he's really asking you to compare like a one sample z versus a one sample t, in which case the big thing is that, or yeah, he's asking you to compare like you calculate a Cohen's d versus a t value. And the main thing is that the t value will factor in the group size, where Cohen's d will not. Which is in many ways the main strength of Cohen's d, is that it allows us to talk about effects independent of the type of research you did, and instead just to say, well, based on how much the population is going to vary, what amount of the population variance can you explain or can you affect with your intervention or with your treatment or whatever it is you're doing. Like we want to make you learn more words, so you learn much more and generate words than read words, and that effect size is like 0.8 or something. So it's like that's a large effect. The amount people would remember, that natural variation, we can improve your score by almost 1 standard deviation.
Okay.
Just by doing this different procedure.
Okay. And then the next one, I have 2 more questions. So number 37, okay. Number 39. So for 37, like, how do you identify which is optimal to address a given research question? Null, confidence, or effect?
I'm trying to think what he means here.
Like null, it says null hypothesis test, confidence interval, or effect size. So how do you decide which one's the best, like for that experiment?
Generally, it'll be what they care about. Like if they just want to know that this is like, so for lots of things like theoretically important stuff, we're not really interested in how big an effect it had, but whether or not it does have an effect. Like if I have some theory about how memory works, so let's say I have a theory about color affects memory and that the color in which you see things will affect how much you remember it. Then all I really care about in that case is the null hypothesis test, because if I find a difference, that tells me, okay, it does look at it like it has an effect. So that tells me that color plays some role in memory, because when I change the color, the amount people remember it changes.
And then
so
maybe
that's to verify something is there. Where confidence interval is more to say like when you're interested more in the magnitude of the effect, which is also kind of effect size. Confidence interval has more to do with precision. Like, let's say I really want to know how depressed students at UCLA are. So I'm like, I'm a person who works at UCLA who's in charge of keeping students happy. So in that case, really what I want to know is the confidence interval. Like I want to have a really good estimate of how the students are currently doing. Like, because I want that value. Like I want to be able to report, okay, this is the average anxiety level. This is the average depression level. This is the average like number of friends that each person has. So let's say my job is to just know this stuff. Like, right, we found out recently someone published a study saying that if students have on average at least 10 friends, then they do much better in college. So then I want to know, do UCLA students have at least 10 friends on average, or 10 close friends? So I could do this sort of study, collect as much data as I can, and build a confidence interval around where the true value lies. And if 10 is in there, then I'm like, okay, good. We meet this criteria. Like we're in the region that we want to be in.
And this is what
confidence intervals.
directional because due to previous research?
Well, so confidence intervals generally are not directional because what we're just doing is trying to describe the sampling distribution. We're just saying, here's what all the scores are going to be. If we take the center value, go up and down, if we're talking about Z's 1.96, right? So it's negative 1.96. 95% of the scores are going to be in that region. So if we want to know what the true value here, what's mu, we'll draw a confidence interval to say, okay, these are the real population values, but we don't actually know what they are. Like, we're taking a sample. So we're going to take our sample, plus or minus, let's say in this case we know sigma. So 1.96, because we care about 95%, times sigma. Square root in. So this is like how good of an estimate we can produce. So confidence intervals are generally if you really want to know a value of something. Like I want to know what mu is for this population. Then confidence interval is the most important factor.
This
Where
would be
effect
like
size is like how much did I affect them?
You would want to know like from medication because that's important because it can affect someone's health, and you would want to know the confidence interval so that you can be sure that the results you're presenting are right.
The confidence interval is not so much that. So medication, it's like that's usually comparing differences more often. It's medication is this better than the current medication, right? So what's the effect size as compared? Like let's say I compare chemotherapy to my new cancer drug, and I want to know what's the effect size relative to the cancer drug. Like the population of people taking, or the population of people getting chemo, and they have a natural variation. And now you have a sample that's different from it. But what I want to know is what's the effect of that difference? Like how much of the natural variation among chemo patients can you explain, or can you move them with your new intervention?
So you would want Cohen's d because they're not on maybe the same scale because they're different.
Yeah. But generally, Cohen's d is just if you want to know how much should I care about this effect. Like null hypothesis testing would just tell you this effect. There is an effect, which means statistically these do not look like the same thing. But that doesn't tell us at all how much we should care about it. But if you're very interested, like in a theoretical researcher, like I think this thing, like I think listening to music plays a component in remembering. So if I change the music, if your memory changes, then that tells me it does have an effect on your memory. That, maybe there's a competing theory that says it doesn't affect your memory. And I think that it does. So I can do a test and do null hypothesis testing to tell me, oh yeah, it does. Statistically, you don't look the same when listening to music as when not listening to music. Therefore, music must have some effect on your memory because it's making you measure differently. But it doesn't tell me that it's important. It just says that it's a component. So that's where null hypothesis testing is more important. Because we just want to find, did it matter at all to do this? But if you want to do like treatments and say, well, how much should I care about this treatment, or which treatment should I choose amongst 5? Effect size is a much more important measure because it tells you here's how much you've affected them relative to how much they were just going to randomly vary. And confidence interval is very good for getting good estimates, or if what you really care about is that the estimate is correct and that you want to know, like, if like schools need this all the time for like federal funds say we need to have at least this many, they need to get X on a test score. So build a confidence interval around what the true value of the average test score is at UCLA. And if we're above some number, we get extra federal funding. So there, you don't really care about, you're not testing against something. You just want to know, are we in the range that we need to be? In which case you really want the confidence interval to know, like, okay, with 95% certainty, we can say that we are in the range we need to be.
Okay. And then my last question is 39, which is about pooled variance estimate. Okay. For basically, like, what is that telling you?
Like, pooled variance is the variance of the population. And like pooled variance isn't any different than variance. So whenever, like, this is the very beginning of the class stuff now. Like, so here is mu, and then this is sigma, and then variance is sigma squared. So this is all pooled variance is. Pooled variance is an estimate of sigma. So S pooled.
But when would it be important to know the variance? For like what sort of question would be asked that you would want to answer in variance?
So the only reason we really need the variance is that when we're doing the independent samples t-test, or when we need to calculate this thing, so S sub x bar minus x bar. So when we want to calculate this, actually, this is the measure we care about. But to get there, we need to take the square root of, this other number. So the reason we want pooled variance is because we need to get pooled variance for the population, so we can add the variances of the sampling distribution. Like, it's a weird case. So what happens is we always talk about going from the population. So right, this is our population, and then this is our sampling distribution, and this is sigma square root n. So this is the standard error. But what we don't talk about is this sampling distribution also has a variance. And that is found by squaring this number, which gives us sigma squared over n, right? Because you square both the top and bottom. So this is what pooled variance is. Or pooled variance, to get to this thing, we need pooled variance. So we take pooled variance, and then we s squared pool, and divide by n, and now we have a variance of our sampling distribution. And the reason we want that is because we have to add them together.
For what?
To calculate this thing, right? So this
for an independent samples t-test.
Yeah.
So basically, it's because you're calculating two of them that you have to add together.
Yeah, because you can't add standard deviations like you can add variances. Like the variance sum law says that you need to be working in variance. So that's why we do this thing. We're adding these two variances together, which that ends up being this. So when you add the two variances of their sampling distributions, you get the variance of their differences. And then we use that down here, where we take its square root, and that gives us the standard error of the differences. And all that was done for, I think I have a slide on this. So x bar 1 minus x bar 2 follows a t distribution with a center at 0. And that is our spread. So this is all, we did all these steps to basically get to this point, which is like, okay, now we've set up the problem in the way we're always used to working, which is we have an expectation of the center and a spread value, and that's why this is on the bottom of the, when you calculate a t, t is equal to, in this case, x bar 1 minus x bar 2. So that's the thing we're observing. This is the expected difference of 0. And then this is, that thing. That's the spread of all these values.
Okay. Okay.
So it's a bunch of steps, but the point is to be able to describe our expectations of the differences.
Okay.
So we do all that to get there.
Thank you for your help. Somebody else joined the chat, so.
Awesome. I will set you free.
Questions, but yes, because I've been on here for a while. But thank you so much for your help.
No problem. See you tomorrow. Good luck in the exam.
Thank you. Bye.
See ya. Take care. Hey, how's it going? Okay, I don't hear anything, but I saw you unmute yourself.
Sorry, can you hear me?
Yeah, I can hear you now. So what's up?
Okay. Do you happen to have the slides that we used in class as well?
Yeah, I have all of them.
Okay. Yeah, I'm looking at the day 10 ones.
Day 10. Okay, I have those open now. Which slide number do you know?
Okay. Well, I have a couple questions going down the line. So I'm looking at the orphan perception study first.
Okay.
Yeah. So would this one be like a one-tailed or a two-tailed distribution?
So here it's a one-tailed. So if you look at, I can screen share here. How do I present this screen? There it is. Okay, so right here, this tells us that it's one-tailed.
Okay. Then, hang on. It's one-tailed. But then later on, when they calculate the confidence interval down there, they use the value for the two-tailed test.
Yeah, so the confidence interval is always for two tails. Like the confidence interval is basically it's equivalent to doing a two-tailed test.
Uh-huh.
But when you're calculating the confidence interval, you don't ever do like a one-tailed confidence interval. Because so I had some slides on this in like discussion a few weeks back, but I think it's worth repeating. So when we're talking about the sampling distribution, oh, this is so much nicer not having to make these in PowerPoint. So when we're talking about the sampling distribution, right, this describes our expectation for all groups. So we take group means and they're gonna fall in all these regions. And the height tells us the relative probability of finding any given group mean. Mm-hmm. So what we're really doing when we're drawing the confidence interval, if you just imagine this is the population, what we say is go to the center and go up by, in this case, if we're using Z, go up by 1.96. So let's call that 1.96. And it's 1.96 times this thing, right? Because that's how it ends up working. I say I can show you better down here.
Obviously, I still see the screen.
Oh, sorry. Yeah, I am trying. Okay, that's right.
Yeah. Okay.
Okay, so Z crit times. So what we're trying to do is capture where the score is going to fall. So if we do this, like, right, there's a value there. There's a value there. Mm-hmm. So the reason we're doing this as a confidence interval is and the reason it's actually finding what we say it finds, because the confidence interval says that if you do this process 95% of the time, when you do this process, the interval you draw will contain the true population mean. So I think it makes much more sense visually. So let's say we get a value that is exactly the mean, right? So we're going to go up this much, which is lined up with that, right? And we go down this much.
Right, okay.
So that score captures mu. Exactly, right? Mu is in there. But this is our expectation. So if we get a score anywhere within this range, what you'll notice is that we will always capture it. So if we get a mu here, or we get an X bar score right here, we're going to go up this amount. But see, we know from here to here is 1.96. So if we go down 1.96, we're already to the left of it, right?
Yeah.
So we captured mu again. And the problem is sometimes we're going to get, right? So we know 2.5% of the time we're going to be greater. So we're going to get, actually, let's do it in a different color. So these are the ones where we miss mu. So if I'm outside of that little region, we're going to go up. Let's say it goes off to the edge. And this goes down 1.96 and doesn't quite capture mu. So I miss it there. And the rate at which this will happen that we miss it is 5% of the time. So sometimes we'll be low, right? We'll be over here. We go that way. And I think it also makes more, actually, it'll be like right here. In class, he showed it, I think, in a slide that a lot of people didn't understand. He has a slide that looked like this, where he drew a red line and then has all these lines that go up and down. Mm-hmm. What he's actually showing you is what I was showing you, which is that when you draw this thing, if this is the true, oh wow, I missed mu by a lot. But if this is the true mu value, then you can just watch over time as you generate more and more confidence intervals, and 95% of them will contain mu and 5% will not.
Okay.
And the reason it works is because of how the sampling distribution is laid out. Like anytime we're basically beyond the rejection region, we draw a confidence interval that fails to capture mu, which is why this is equivalent to doing a two-tailed test. Okay. Because, right, it will give us the exact same answer. If we know the upper and lower bounds of our confidence interval and they ask me to do two-tailed test, if my number's outside here, I already know the conclusion. I reject the null hypothesis because it isn't, it isn't one of these scores that's going to happen 95% of the time. It's one of the scores that will happen less than 5% of the time.
Okay. Yeah, I get that. Okay. Okay. After that, on the slides, when it goes down to the independent samples t-test part,
okay.
Yeah, I may be like missing something, but is there a reason why we didn't calculate the effect size and the confidence interval for that example? Or?
No, there shouldn't be. I mean, you can do it the same way. I mean, you don't use Z, you use T instead. So you have a T critical, which will be dependent on degrees of freedom and alpha. And then this is S over, actually you can use S sub X bar, right? That's the nomenclature we use.
Yeah.
That's equivalent to S over square root N.
Yeah, okay. I was just wondering why they didn't calculate it in the example, but we could have done it as well. Okay.
Yeah, you could have done it. It wouldn't have changed anything.
Okay, then okay, so when it goes down to the the dependent samples t-test with the family and therapy anorexia, that's why I was slightly confused.
Okay.
Because I didn't understand like how they how you derive the null hypothesis and the research hypothesis from the example.
Okay, let's see. Mu d is greater than 0. D is less than 0. Oh, because they're making a directional. Because here's what we're actually doing with the dependent samples. So it's very similar to independent. It's just a different research design.
Okay.
So actually, let me read a little bit more here. Okay, so wait, what was your question again? Because I want to just get to that part so I don't.
How do you find the null hypothesis and research hypothesis for this particular question?
Okay, so the null, like if you think of a dependent sample, so here's a dependent. What you're doing is, so let's say this is like these numbers are just different participants. So these are our participants here. And then we have two conditions. We have condition A and condition B. And so when you're in condition A and B, in this case, everyone actually is in the study. So everyone's in both conditions. So let's say I want to see how many words you remembered of some list. So A and B are just two different ways of showing the list. Here you remembered 10. Here you remembered 7. Here you remembered 11. Here you remembered 10, 13, 8, 14, 16, 12, 10. So what we're doing is not so much, we don't care about the raw numbers. We want to know the difference score. So these are the differences. So that is, we can just do A minus B. So it's 10 minus 7. The difference is 3. So that tells me how much greater A was than B. And I can do the same here. So your difference score is 1. Your difference score is 5. Difference score is -2. Difference score is 2. And then what goes into computing it is, this is the value we want, which is just the average difference. So take every difference score and then divide it by the number of scores we actually have. So that's the real, like the thing we care about with the dependent measures test. And so what we're really asking is this question. We want to know, like the null in this case, so if you presume A and B are not any different, so here's A and here's B, and then you're a participant, let's say you get 10 in A, what would you expect to get in B if A and B are not different than each other? 10. So your difference score should be 0. So what we're always expecting is a difference of 0. Like when you're doing these dependent tests, generally what you're looking for is this a non-zero difference?
Okay.
So if we just remember that the order we did was A minus B. So when you're doing a two-tailed, you just want to know, is this 0? Like, is the average difference score 0? And how different is it than 0? But you can also make directional hypotheses. So if I think that A is going to be greater than B, what would I predict on these differences? So let's say if A is supposed to be greater than B, what would you get in B here?
8.
Yeah, 8. So now the difference score we observe is -2. So really what we're looking for is, you can imagine, just keeps going. The average difference score should be less than 0, because that's the direction we're predicting. If we predict the opposite, that B is going to be better than A, then we would predict this is 8 and that's 10, and we get a different score of 2. So then in the other direction, we would presume an average difference score that's greater than 0, which tells us that B is doing better than A.
Right, okay. So in this particular example, it says, is family therapy effective in increasing weight in adolescent populations?
Okay.
So
yeah, it's probably easiest to like in my head, I draw these things out. So therapy and the control was just nothing?
No, there's no control. Is it effective in increasing weight in populations?
Oh, so is this saying that, oh, they're doing a before after, aren't they?
Yeah, before after, yeah.
So we'll do pre and post here. So pre and post. So if we want to know, let's say you start at 100 pounds. So we want to know is it effective at increasing weight?
Is it effective at increasing? Yeah.
Okay, so if it's increasing weight, what would go in the post?
120.
So 120.
Or whatever.
And if it's pre minus post, then we'd expect -20. So that's why we want to know a mean difference score less than 0. So that's the direction we're predicting. We're predicting that when you look at pre versus post, so pre score minus post score, we get a negative number when we're actually increasing weight. So then our prediction becomes the average difference score is going to be some number, not greater than, some number less than 0. Because if the average difference is less than 0, then across all the people in our study, they're getting heavier.
Oh, I see. Okay.
Yeah, so it makes more sense. Like to me, whenever they ask me those questions, I don't try to like work it all in my head. I just write, okay, if you're predicting this, then I'll just make up a data point here. What data point should go there? What would be the difference? Well, that's the direction I should predict. If I get a negative number, I'm going to predict that it's going to be less than 0. If I get a positive number, I predict that it should be greater than 0.
Okay, but if it's two different, well, I guess they're dependent, but there's two different samples, like not pre and post. If it's A and B, is it always A minus B, or can you do B minus A as well?
You can do either way as long as you just keep it straight. Because what happens is that you just have to keep track of which you did first and keep subtracting in the same direction, right? So if this is A and that's B, and here you're calculating your different scores one way, and then you get you'll get some t value. If the t value is when you calculate, I guess no, here it would actually always work out, right? So you just get a number that would always produce an average difference score. Say, is that different than 0? And then divide by, what are we calling it here in this book? I think it's S sub, yeah.
But wouldn't the hypothesis like change direction if it's A minus B or B minus A?
Well, not the hypothesis would change direction, but as long as you test the correct direction, right? So your hypothesis could switch. Like in this case, if we didn't do A minus B, we did B minus A, then the difference score here would be 20, and we predict that it should be greater than 0.
Okay, that'd be the research hypothesis. Okay, I see.
Yeah, so it just depends on, you just have to make sure you keep doing it in the same order. What you don't want to do is calculate differences one way and then switch your hypothesis to test the other thing. Because then this will produce, right? So if we do find a difference, in this case, if we're doing B minus A, then our real hypothesis is this one. We'd expect a number greater than 0. And then we calculate all this, and we'll get some positive t-value, right, if we actually do have that. And then we just know that, okay, because it's directional, we look up the t-value. And when we look up the critical value, it'll always give us the positive number. So we need to remember just that to compare against the right criteria. So if you think of it like this, when you look up the t-value, the t-crit will just be some absolute value of a number.
Yeah. So when do you use the negative? That was another one of the questions.
When do you use the negative t-value?
Yeah, because they in that same example they use the negative t-value instead.
So the reason they use the negative in the case the pre versus post is because they were doing pre minus post. So they expected -20. So then what you're saying is if these are my expectations here, then I want to know if, because I'm testing directional, I'm not doing two-tailed, like here's the center. So I want to find the region where 5% of the scores are smaller than it. And then everything to the right is 95%. So that's why I use a negative value, because 0 is in the center. So if your critical value is expected, you're expecting a low value, or you want to find low values, then you set it to be negative.
Okay, so if it's directional towards the negative side, then you have to use a negative t-value.
Yeah, because you're expecting this thing to produce negative numbers.
Okay, I see.
So you want to test, are they negative enough to convince me that they're statistically different?
I see, okay. Okay. Let me see if I have anything else to ask. Okay, yeah. So when they were calculating the effect size in the slides, it said that using the standard deviation of the differences is highly controversial, but the standard deviation of the pretest is much better.
Yeah.
But why would that be?
So you can imagine treatments where, because really here's the question, especially with pre and post. So if I'm saying this is how much the population varies, so just raw, again, that's probably better than you. So this is in general how we can, just to draw a picture for ourselves of how variable the population is. So this is before they've done anything. So this is basically everyone with anorexia in this case. If you have a group and then produce a value that their weight is unexpectedly high, right? So you get something over here. Wait, sorry. What was the question? I've already started answering and I've lost the thread.
Why is the standard deviation of the pretest better than the standard deviation of the difference?
Oh, okay. So the standard deviation of the differences is
like
it's less variable than here. Yeah, S sub D.
S sub D, yeah.
So the reason is when you think about effect size, what it's telling you is relative, or the measure we're generally trying to get with effect size is relative to the population and their natural variation. How much of an effect did you have? So we want to know your score minus the, in this case, the population expected difference is always 0, right? Or actually, not that. So minus, actually, yeah, that's correct. Although I guess we wouldn't call this an X bar, we call this a D.
D bar, yeah.
Yeah, so D bar, and then we'd expect to find no difference. But here's how much the population is already varying on its own. And sometimes when you have this paired samples test, what happens is that the variation gets smaller than the natural population variation. So what it makes it look like the effect matters less, when really we want to know practically, like the answer you're trying to get with effect size is relative to what's already happening in the world, how much can you change that? And so you should use the properties of the world sort of before you started doing this dependent measure stuff and just say, how much do people vary? And then how much of your change, how big is your change relative to the natural variation of the population, not relative to the differences expected by randomness purely.
Right. So you're looking at it relative to the original situation. Okay.
Yeah, like, we increase their weight by 10 pounds. If the natural variation of weight is about 3 pounds, it's like, oh, that's huge. 3.3 repeating effect. So that had a giant effect on the population, where this value might be, 1.4. And then you say, okay, 10 over, actually, no, sorry. Yeah, so it just distorts the picture. Because now we're taking into account a thing that doesn't really explain the population nearly as well as sigma does. Okay. So this is kind of putting in terms of the population level, what's already happening in the population, how much did you affect them? Where this is kind of distorting it. Because this value is not like a natural, the pre-post value is not the interest in the population. Like, you want to know relative to how people are doing in anorexia, how much can you move them around? Not relative to having done a study on people with anorexia pre and post scores, how much of the variation of pre and post can you relatively explain? It's much more practical to just say how much of the population's natural variation are you explaining?
Okay, I see. Okay. Yeah, I think that's all the questions I have as well. So I'm good for now. Thank you.
Awesome. And yeah, I went through like a whole bunch of that earlier stuff with Taylor before, so if you want to watch this later, there's lots of good stuff in there too.
Oh, okay, sure. She was on for a while, wasn't she?
Yeah.
Okay, sure. All right, thank you very much. See
all right, cool. Take care. See ya. All right, it's about 12, so good luck on the exam, everybody. I'll post this online in a few minutes.